Okay, let's start the session. Good evening, everyone. This is live discussion session number 4 for Basic Thermodynamics, Classical and Statistical Approaches, a NPTEL course. And uh, myself, Akash Gutal. I am PhD student from Department of Chemistry, Indian Institute of Technology, Jodhpur. So before starting this session, uh, before starting the problems, we will first as usual, we will revise the last week uh, content from the course. So what we have done in last week is uh, week number 3, week number 4. Yeah. So what we have done last week is we have seen the enthalpy change is nothing but the QP, and can be defined as heat measured at constant pressure. Heat measured at constant pressure. And it, it is it is defined that one can only measure the change in enthalpy. Right? And this change is actually uh, measured in terms of with respect to one reference state, and we need to define that reference state. So we'll call it a reference state, right? And this is also termed as standard state. So any substance in its pure form at 1 bar pressure and at specific, sorry, at specific temperature is termed as the standard state. Okay. And standard enthalpy change can be given as so the definition of standard enthalpy change can be given as initial, we are considering our system is at initially at 1 bar and certain temperature T. So this will called as our standard state. And we know that at final state, some uh, at the same 1 bar pressure, or whatever the state variables P and T, V, whatever the state variables, and this change we can say as standard enthalpy change. Okay. This transition between these two, the change in enthalpy between these two is called, can be termed as standard enthalpy change. Okay. Then we have seen that the statement about how the standard enthalpy uh, of the elements is calculated. So standard enthalpy of formation of element in its natural form is zero, right? And it can be termed, which means in its natural form, in the sense, suppose we have nitrogen. Nitrogen exists as a sorry, nitrogen exists as N2 gaseous state. So the enthalpy of formation for N2, enthalpy of formation for N2 is N2 gas is zero. And one can define by this value of delta H. If it is less than zero for a given reaction, then we will conclude that released heat is released, and if it is greater than zero, heat should be given to the system. So there are, we can define the different changes and in the given chemical chemical or chemical compound, and we can, for that every changes, we can define its enthalpy change, such as suppose there is a vaporization or fusion or sublimation. So for every these processes, we can define the delta H or the enthalpy change for these processes. And uh, so, so delta formation enthalpy change for is standard enthalpy of formation. And this standard enthalpy of formation we can define so, or we can say standard enthalpy of reaction is summation of products into its stoichiometric stoichiometric ratio into product formation minus reactant formation with their respective stoichiometric coefficients. And so for reaction, standard change in enthalpy for the reaction can be given as product enthalpy of formation of products minus enthalpy of formation of reactants. And these equations are actually balanced by with their stoichiometric coefficients. So I will introduce one new slide. So next thing we learn about the Hess law. So Hess law is about constant heat summations. So what Hess law says that enthalpy change of an overall reaction is sum of the standard enthalpies of the individual reaction. So, so this is termed as Hess law. And there is another law we have seen that is called Kirchhoff's law. And it states that standard enthalpy of reaction at temperature T2 is equal to standard enthalpy of reaction at temperature T1 plus integrating T1 to T2 change in standard enthalpy of reaction in change in their respective heat capacities into dt. So, and we can define the Cp delta R Cp standard. We can define it as difference in the molar heat capacities weighted by stoichiometric coefficients. That appear in the chemical equation. So we can define it as delta CRCP is equal to summation of J to Ej delta RCP standard for all J's. Right? And then we have seen the second law of thermodynamics. I will start in on new slide. Then we have seen the second law of thermodynamics. the second law of thermodynamics. So, what are the basic statement about the second law of thermodynamics is that the entropy of system plus surroundings always increases. Hmm. And after that, have seen what is the Carnot cycle. So Carnot cycle, we know it is a reversible cycle in which we are having four processes. So the first one is isothermal expansion. Then we have adiabatic expansion. Then isothermal compression. Then adiabatic compression to the initial state. Okay. So this is the isotherm. This is the adiabatic process at temperature. Oh, sorry. At temperature T1, this is adiabatic process. Sorry. This is also isothermic process with at temperature T2. This is a adiabatic process. Okay? And we have defined that the efficiency of Carnot cycle or in term in that sense any engine is nothing but efficiency is 1 plus q3 by q1, where we can say the q1 is this, which is getting inside the heat getting inside the first process in expansion, and a to b for the process a to b, the heat getting inside is q1, and for c to d, its heat is getting as q3, so we call it q3, and the ratio between two, 1 plus q3 by q1 is nothing but the efficiency. So it can be written in terms of temperature, 1 minus T3 by T1. So suppose one engine is operating between a hot reservoir versus a cold reservoir, we can say, and it is operating and it is doing some work. Suppose the heat taken from hot reservoir is QH and heat sent to the cold reservoir is QC, and we can define that efficiency is nothing but 1 minus QC by QH. So this is nothing but efficiency we can get 1 minus TC by TH, cold divided by hot temperature. Okay. So After defining the Carnot cycle, we define what is the uh, term state function called entropy. So the entro so one so what we get from the Carnot cycle is that one can get the Carnot cycle from the Carnot cycle is that one cannot make engine make an engine with efficiency 1. So one cannot make an ideal engine which having efficiency 1. Okay, that is also one statement for second law of thermodynamics. Fine. And what we defined as the entropy. Most important concept that second law of thermodynamics gives is the entropy. So dq reversible, it's defined as the heat absorbed by the system at reversible process at constant temperature is called entropy. Definition of entropy. So after that, we have seen what is the Kelvin Kirchhoff's law. Sorry, Kelvin Planck's law. So what this law states that it is impossible to construct any uh, heat engine where it can take the heat uh, from only one source. So we can't construct any engine which is only takes the heat from one source or takes and gives the heat to one source. So it is not possible. So this so for that we must require two sources. One is hot temperature source and one is cold temperature source. So we can't construct any engine which is having only one heat source. So it can be this law can be states written as it is it is impossible to make a thermal engine that works in a thermodynamic cycle and generate power while it has heat exchange with only one source or only one thermal reservoir. So it's impossible to construct such a heat engine. So this ends the revision of last week. So we will go towards some problems. So here is the problem. So to calculate delta H of the reaction. So CS2Cl2 gaseous, this reaction is given. It's forming C solid, that is carbon solid, plus 2H gaseous plus 2Cl in gaseous form. Give the bond energy CHCCl. So it's given that the bond energy CHCCl is 400 kilojoule and 320 kilojoule respectively. We need to find out the enthalpy change in the reaction. So we'll take out first the given things. Sorry, it's when the given things are the bond energy of CH, the bond energy of CO. So bond energy of CH is 400 kilojoule, and the bond energy of CCl is nothing but 320 kilojoule. So we need to find out. We have the equation CH2 Cl2 gaseous is equal to solid plus 2Hg plus 2Cl gaseous. So we can write its delta change in enthalpy equation for this reaction is equal to, we know, summation product P delta minus reactant. Okay. So we have in the product C. So summation is it's 1 into delta H of carbon plus 2 into delta H of hydrogen plus 2 into delta H of Cl. This is in gaseous form, this is in gaseous form, this is solid form, and total minus 1 into. So So we have the bond energies. So we know the given compound is CH2Cl2. So we have two CH bonds, two Cl bonds. So we can say that 2 into bond dissociation energy of CH plus 2 into bond dissociation energy of CCl. So its bond dissociation energy, according to Hess law, we can say uh, so its bond dissociation energy we can consider at it's a change in enthalpy. It's enthalpy. It's a delta H for the reactant. So by doing it, the calculation, and we know that standard delta H formation is zero for in it's in for the elements in their uh, natural form. So all of this uh, for carbon, hydrogen, and chlorine, because they are existing in their elemental form, their delta H will be zero minus 2 into bond dissociation by CH is 400 and plus 2 into bond dissociation is 320. So that will gives you in kilojoule 400, 800 plus 640 is nothing but 1440 kilojoule. Answer option is number 2. Right. So the next problem is how much heat will be required to make 2 kg of calcium carbide CaC2 according to the following reaction. CaO solid is given plus 3 carbon in solid state is given is giving forming a CaC2 compound, calcium carbide plus CO, gaseous carbon monoxide. So the heat of formation of CaO in solid state, CaC2 at solid state, and CO in gaseous states are given. And we asked what is heat required to make CaC2. It's nothing but we asked about the enthalpy change of this reaction. That is the formation of CaC. So we will take out the given things. So it's given that heat of formation for CaO is nothing but minus 151.0 kilocal. Formation for CaC2 is nothing but minus 14.0 kilocal. Delta H formation for minus 26 point, oh, sorry, formation for CO in gaseous state. So its state is solid. This is in solid state. Is given minus 26.0 kilocal. So we know delta H formation is nothing but delta H formation uh, summation of product into delta formation of product minus reactant delta FH, formation of reactants. So this will give you, for this equation is nothing but 1 into delta FH, formation of CaC2 gas state, plus 1 into delta F, formation of CO, and minus 1 into delta H, formation for CaO in solid, plus 3 into delta, formation of carbon in solids, right? And we know for values of CaC2 is nothing but minus 14 plus 1 into delta H formation for CO is 26. Let me write in sign, minus 26.0 minus 1 into delta H formation of CaO. What is the CaO formation? Is minus 151. And we know that delta H formation for element in standard state is 0. It will be 3 into 0. What will we get? Is 14 into 26, 1 cross and 1 cross 151, which is nothing but 26 plus 14 is minus 40, and minus minus will plus 151.0, which gives rise to 111 kilocal, right? Let me add one new slide. Excuse me for just 2 minutes. So I directly right here. Okay. So we got answer is 111 kilocal. So you need to convert into its question was asked in the question is asked, actually we need to calculate it for 2 kg of CaC2 in solid form, for 2 kg, right? First we will calculate for how many, for moles. So in 2 kg, which means 2000 gram, the number of moles for CaC2. The molecular weight, if we calculate, calcium CaC2 is nothing but 64. I think it is 60. uh, 64.078. So if we divide by 64.078, we'll get its mole, and the mole is 31.121. And we multiply this by 1 to 1, we'll get it for 2 kgs. This is for 1 mole, 111 kilocal. So for 31 mole, we will get 3468.75 kilocal. This is for value for 2 kg. So delta H of a reaction. So the answer should be 3468.75 kilocal. So the fourth question is, in the Carnot cycle, if heat rejected from the system Q2 is 0, then the net work done is Q1 and efficiency is equal to 1. The heat is exchanged only with only one reservoir. The third statement is it violates the Kelvin-Planck law and all of the above. So the statement is, in the Carnot cycle, if heat rejected from the system Q2 is 0, then the four statements are given. So that we know that heat rejected is in Carnot cycle. If we plot PV diagram of Carnot cycle, A to B is isothermal expansion, B to C is adiabatic expansion, C to D is isothermal compression, and D to A is adiabatic compression. So what they are talking about Q2. The Q1 is the heat get inside when the isothermal expansion happens, and Q1 is, and the Q2 is heat is rejected in isothermal compression. So they're asking if heat rejected from the system is 0. If Q2, whatever it is, Q2 is 0, then net work done is Q1 and efficiency is 1. So whatever the Q1 heat is getting inside the system during uh, that isothermal expansion is actually converting into the totally into the work, and that thing is actually stating that all Q1, the first statement is stating that Q1 is converted into work, and this is right. And the efficiency is also 1, because we know the efficiency of the Carnot cycle is nothing but 1 plus Q2 by Q1. And Q2 actually is negative quantity, and if it is 0, then your this term will become 0, and nothing but your efficiency will be 1. So first statement is correct. The second statement, heat is exchanged only with only one reservoir, and we know by as we know the statement of that we have seen, uh, that Kelvin-Planck statement. The Kelvin-Planck statement that it defines that it is not possible that if you construct any engine which is uh, getting heat only one source and rejecting heat only one to the one source, that source only. So it is not possible for generating uh, work from getting heat from one source and rejecting into the one source, the same source, because the temperature will be the same. And because of that, heat is exchanged only with one reservoir. See, this is ideal condition, but this is also true. It violates the Kelvin-Planck law. And the second statement is actually the Kelvin-Planck's law, and this comes from the Kelvin-Planck law, which and it gives the third statement also true. So the answer should be all of them. The next question: a perpetual motion machine type 2 violates. So It's given that for the first option is given first law, second law, second is second law, third option is third law, and fourth option is zeroth law of thermodynamics. So we asked the given a perpetual motion machine of type 2. So we need to know first, before solving this question, what are the perpetual motion machine. So the perpetual motion machine is, we call it as PMM. So perpetual motion machine is ideal machine. Generally, we can define it as if we supply energy to the perpetual motion machine, it will convert that energy totally into the work. So this is the ideal type of machine which has efficiency 1. So there are nearly 3 types of perpetual motion machines which people have thought about. So perpetual motion machine of kind 1 is, we can say, it's actually defined as it produces work without supply of energy. What I defined perpetual motion machines earlier is it's one kind. So these are hypothetical machines. These are never possible because it violates one of the laws of the thermodynamics. But uh, this is only generated from only thought process. So the perpetual motion machine of kind 1 is actually produces the work without need of energy. So this is impossible because it violates the first law of thermodynamics. Totally violates the first law of thermodynamics because first law of thermodynamics says energy cannot be created and cannot be destroyed. So this PMM of first kind is actually uh, doing work without getting energy from anywhere, which means it is uh, violating the first law of thermodynamics. So perpetual motion machine of kind 2 is of, suppose it converts the given energy totally into work. So perpetual motion machine of kind 2 is actually converts the given energy totally into the work, which means this kind of machine is actually follows the first law of thermodynamics because first law of thermodynamics actually states that for the given, if you it states about the work and energy equivalence, and but the first law is applicable for the PMM kind 2 machines. It is following the first law, but it violates the second law. How? We will see. So it violates the second law because there is no machine which can convert given energy to totally into work, which means there is a no machine which is having efficiency 1, and that we know from the second law. We can't construct a machine which can take for which can take energy E and totally convert that energy into work. So this is PMM of kind 2. It follows the first law but violates the second law. The third machine is PMM kind 3. PMM perpetual motion machine of kind 3. This perpetual motion machine it does work with by cancelling out, or we can say, or we can say it's we can define it in another way, is that the machine that eliminates friction from the system, friction, or we can say, and other type of disruptive forces. So the machine that eliminates the friction or other type of disruptive forces from your machine. So this is also never possible. If you construct a machine which will be having a noise, it will be having some uh, dissipation of your energy in form of heat, in form of radiation, some kind of dissipation of, or what we can say, throwing off the energy outside of the given machine without converting into the work. It happens in general kind of machines. So that can't the total the friction inside your machine can't be eliminated. It always there. In You can reduce it, but you can't eliminate it entirely. So this is the PMM of kind 3. So these three kind of perpetual motion machines are there. So this question is asking about the type 2. So the type 2, it's actually violates the second law of thermodynamics. The question number 6 is, according to Clausius statement, it is impossible to construct a device that can transfer heat from a cooler body to a hotter body without any effect. And the second statement, it is impossible to construct a device that can transfer heat from a hotter body to a cooler body without any effect. It is possible to construct a device that can transfer heat from a cooler body to a hotter body without any effect. And the last is none of the mentioned. The first, so we will read the first statement. If it is impossible to construct a device that can transfer heat from a cooler body to the hotter body without any effect. So from cool body to hot body, the heat never transfers. Only transfers spontaneously from hotter body to cooler body. So this is the correct statement. Let's see if the second statement is right or not. It is impossible to construct a device that can transfer heat from a hotter body to cooler body without any effect. It is possible actually, so this statement is false. And the third statement is, it is possible to construct a device that can transfer heat from cooler body to hotter body. So cooler body to hotter body without any effect. Without any effect, it's not possible. So this statement is also wrong, because we need to do work to transfer uh, the heat from cooler body to hotter body, which is we do in refrigeration. So the next question is, the Carnot engine has to exchange heat with dash dash energy reservoir at dash dash different temperatures to produce net work in a complete cycle. The options are 1 1, 1 2, 2 2, none of the mentioned. So the answer should be, the Carnot engine has to exchange heat with two two energy reservoirs. Okay, the energy reservoirs must be two. There must be two different temperature gradients at two different temperature gradients. Yeah, two different temperature to produce a network in a complete cycle. So the answer should be two. And question number 8: Carnot cycle is a reversible cycle. Yes, Carnot cycle is reversible cycle, and the statement is true. And question number 9: The correct sequence of the processes taking place in a Carnot cycle is adiabatic, adiabatic, isothermal, isothermal, adiabatic, first option. The second option is adiabatic, isothermal, adiabatic, isothermal. Third option is isothermal, isothermal, adiabatic, adiabatic. And the fourth option is isothermal, adiabatic, isothermal, adiabatic. So the general Carnot cycle that is defined by Carnot is having the first process is isothermal expansion, the second process is adiabatic expansion, the third process is isothermal compression, and the fourth process is adiabatic compression. So this is the Carnot cycle. So the answer must be isothermal adiabatic, isothermal adiabatic. The last question, the 10th question is crossing of two adiabatic lines will violate the second law of thermodynamics. So we will see crossing means eliminating. So we'll see how this statement is true or false. So we know the Carnot cycle. Right? So we have isothermal process here, adiabatic process here, isothermal process here, adiabatic process here. So this is isothermal expansion. Isothermal expansion, the heat will be getting inside of the cycle, and C to D, the isothermal compression, heat will be rejected from the system. And as we can see, uh, suppose this is Q1 and this is Q2. So we know, so the question is asking about crossing of the two adiabatic lines. Crossing means if you delete these two lines, so what does it violate the second law of thermodynamics? So as we can see, if we cancel out these two lines, adiabatic lines, so we will see these two will become the same. A to B and C to D process will become the same. I mean, and once they become the same, Q1 will the heat gain and loss. There will not be any work. So there will not be any work done by the system. And once there is a Q1 will be the same as that of Q2. And once there is a no work done, that will not be a cyclic process. That will be, but it will not having any work done. So the net work done by the Carnot cycle will be zero. So the statement is giving you it is true. And the most important part will become if Q1 becomes Q2, which means this engine is getting heat from a single source or two sources having same temperature. And we know by the law Kelvin Planck law, by Kelvin Planck law, we know that we can't construct a cyclic machine which is runs in a cycle from only single heat source. And this is actually violation of second law of thermodynamics. That's why this statement is true. So next question is question number 11. Is a Carnot engine operating between two reservoirs has efficiency 1 by 3. When the temperature of cold reservoir raised by x, its efficiency decreases to 1 by 6. The value of x if the temperature of hot reservoir is 99 degrees Celsius will be. So we are asked to calculate the value of x. Fine, we will take out the given things. So we have given that efficiency of Carnot cycle, initially it is 1 by 3. And it becomes when the temperature of cold reservoir is raised by x, or the cold reservoir is raised by x, then your efficiency decreases to 1 by 6. Right? Its efficiency become 1 by 6. So we know the efficiency is Tc by Th. And we once we do increase the cold temperature by x, so let's calculate Tc by Th. We can easily get this. We will calculate what is the Tc by Th. So Tc by Th is nothing but, from this first equation we can calculate 1 minus n1 eta 1, sorry, which is nothing but 1 minus 1 by 3, which is 2 by 3. And so when we calculate for n2, so Tc plus x divided by Th is equal to, it's 2 by 3, and sorry, 1 by 6, 1 minus 1 by 6. This is nothing but 5 by 6. So Tc by Th plus x by Th is 5 by 6. And we know Tc by Th is 2 by 3. So x by Th is equal to 5 by 6. This is 2 by 3. We take that side, minus 2 by 3 here, which will be 6. It's nothing but made a mistake. Gosh. Yes. 2, 3, 4. 5 by 6 minus 4 by 6 is nothing but 1 by 6. So x is equal to, x by th is equal to 1 by 6. So x is equal to 1 by 6 into 99, which nothing but what 16.5 Kelvin. So x is nothing but 16.5 Kelvin. The answer will be option A. So next question is, a thermally insulated vessel contains an ideal gas of molecular mass m, and the ratio of specific heats is 1.4. The vessel is moving with speed v and is suddenly brought to rest. Assuming no heat is lost to the surrounding and vessel temperature of the gas increased by, so the options are given. We need to calculate the temperature increase in the for the vessel. So the CV is given in this, sorry, CP by CV is given. This problem is 1 by 1.4. So we know that CP minus CV is equal to R. And for 1.4, as we know, for diatom, the CP by CV is 1.4. then CV is nothing but 5 by 2R. And so what they are saying is vessel is moving with speed V and is suddenly brought to the rest. And we know the molecular mass is M. So if the vessel is moving with velocity v, then every particle there is moving with velocity v. And its kinetic energy, we can say, is 1 half m into v square. M is its molar mass, molecular mass. And we know by definition that we have 5 degrees diatomic system. We have uh, 5 degrees of freedom. So we know that according to kinetic theory of gases, is nothing but 5 into 1 half R into T is nothing but its heat content at temperature T, which can be equated to its kinetic energy mv square. And so we know 1 half is get cancelled, so T will be mv square by pi R. Option is B. Fine. And the 13th question is a heat engine operates with the cold reservoir at temperature 3 to 4 Kelvin. The minimum temperature of the hot reservoir, if the heat engine takes 300 joule heat from the hot reservoir and delivers 180 joule heat to the cold reservoir per cycle is dash dash Kelvin. So we will take out the given things. So cold reservoir temperature is 324 Kelvin. So we need to calculate the minimum temperature of hot reservoir. If the heat engine takes the Q1 is given, or we get from the hot QH is given, hot reservoir is 300 joule and delivers 180 joule to the cold reservoir. Right? We need to calculate QTH. So we know that QC by QH is nothing but TC by TH. So if we calculate it, QC is 180 by 300. So TC is 324 by TH. We get 324 into 300 by 180 by TH. So this will be also 54. It's say 18, 550 Kelvin. So the answer is 550, also 540 Kelvin. So answer is 540 Kelvin. So the next question is which of the following is allowed by the second law of thermodynamics? So more than one answers are correct. So notice E represents the engine R and R represents the refrigerator, W represents the work. So if you see the first diagram, the T1 is 900 Kelvin and the it's we can say that it is hot reservoir, and this is cold reservoir. Let me just write. And this is the cold reservoir. So if you by seeing watching the temperature, we can tell which is hot and which is cold. So this is hot and this is cold, and heat is transferred to from hot to the engine, which is right, and the engine is doing some work. It's going outside, and some heat is rejected to the cold reservoir. And this is actually a right. So this answer, this is the right option. The second is it's so E is represent the engine. So this engine, the first option is right. The second is T1 is 900 Kelvin, T2 is 200 Kelvin, and heat flow is going from cold to hot, and this is refrigeration, and it is right. This is right, and this is also right. But as we can see, without doing any work, it is transferring, which means it is violates the second law of thermodynamics. So this will not be right answer. And third is the same diagram as the second option, but here the work is done on the system to run the refrigerator, and which makes this third option right. And none of the above is not the option. The correct options are 1 and 3. And the last question, the minimum work required by an engine to transfer 5 joule of heat from a reservoir at 100 Kelvin to 1 at 300 Kelvin is. So this question is about uh, transferring, it's given as an engine, but it is a refrigerator because it is transferring heat from 100 Kelvin to 300 Kelvin, means cold reservoir to hot reservoir. So the work required, so this is case of refrigeration. So we first draw the diagram. I will draw the diagram here. So this is hot reservoir at 300 Kelvin. This is cold reservoir at 100 Kelvin. And this is the engine. Here it is given as engine E. And the work we need to do in order to take heat from cold reservoir to the hot reservoir. And W is the work. So we know that in case of refrigerators, so we will give this name as QC and QH. So we know in for the engine we have efficiency, but for refrigerators we have coefficient of performance, which can be defined as heat taken from the cold reservoir divided by the work done on the system. So this is the definition of coefficient of performance. And this coefficient of performance, uh, we can write. So small derivation, I would like to show how the coefficient of performance and the efficiency of heat engine is related. So beta is equal to QC, and the W is nothing but QH minus QC. which gives you QC by QH minus QC, which gives you QH by QC if you divide it minus 1. And we know for the efficiency is nothing but QC. Efficiency is nothing but 1 minus QC by QH. So this will become 1 by eta. Or we can define that QH by QC is some K. Sorry, QC by QH is K. It's nothing but K minus 1 by K minus 1 is giving rise to K by 1 minus K. Fine. This is just simple relation. Uh, you can define using simple mathematics. So what we have is coefficient of performance beta in terms of we can write. So we have QC by QH minus QC, which can be written as equivalent to TC by TH minus TC. And we have in the question that TC is 100 and TH is 300. So we can calculate coefficient of performance, which is nothing but 100 divided by 300 minus 100, which is nothing but the 1 by 2. 200 by 200, which is nothing but 1 by 2. And from that, we know beta is equal to QC by QH minus QC. It's nothing but is 5 joule of heat is from reservoir 100 to transferred to reservoir 100 to 300, which is nothing but the QC is 5 and QH we need to calculate. Uh, no, QH minus 5 is nothing. We need to calculate is QC by QH minus QC is W. So you need to calculate what is the minimum work required by AJ. So QC by W is given. So QC by W is need to QC by W is nothing but the beta, and beta is 1 by 2. QC is 5, and we need to calculate W. The W is 5 into 2 into 5, that's nothing but 10 joule. So the answer is second, it's 10 joule. So this is the CSIR 2015 question. Fine. So thank you very much for attending the session. We will meet next week, Tuesday, 7 to 9. Thank you very much. If you are having any question, you can ask. So I'm turning off my camera.
If anybody having a question about this, we can discuss.